So, heard y'all like assembly. There you go. Y'all love assembly. And if you don't, well, you're going to. Alright, so I can get the mouse over there. Perfect. First of all, name's Zamal. Work at TrendMicro. Been working there for about 8 months or so. Graduated from UFT. Love that place. But now I am here, and it is very fantastic to be here. Thank you for having me. So, if you could, or if you want to follow along, we have a link to this entire presentation just over here. Or if you want to go to my GitHub, it's over there. And it will help quite a bit. I'm going to be using this as a rough guide for the most part. So if you want a bit more clarification here and there, it will be useful to have handy. Now then, let's get started. So, if I can scroll, there we go. All right, so we all know that computers run off zeros and ones. That's true. Pretty much everyone knows that, I hope. However, what are those zeros and ones actually called? Do they have an order? Do we actually do anything useful with them? Probably, because it does support our modern society for the most part. Now, what we call those zeros and ones is machine language, or machine code. So you can think of code as programming made entirely out of bits. Not even bytes, bits. It's kind of hideous sometimes. And it's not too readable. Realistically speaking, if you take a look at some machine code, it's just a bunch of bytes in a sequence. Going down, very long, not too useful. However, we as humans like reading things. I'm gonna sit down a bit. So we invented assembly. Assembly is just a human readable version of machine code. If you want to understand what a computer is doing, what a program is doing, instead of looking at a bunch of zeros and ones, you can now look at proper statements, which will make life a bit easier. How much easier? Well, it's the difference between this and that. And more accurately, your computer takes a look at it like this. I don't know about you, but if you try to parse that, it doesn't quite make a lot of sense. But to be honest, this doesn't make a lot of sense either. I prefer Intel syntax. So, you have two main things in machine language. You have opcodes, which you can think of as functions, just special bytes representing that we want to run this function. And then you have operands, which are like arguments. This function takes these operands, and you repeat that over and over and over again. And now you have a program using just bytes. You can also take a look at the disassembly listing and opcodes and machine code of any program by calling object on it. And you get a nice little listing over here. Now then, computer memory. Computer memory and the stack are things that get people quite confused. We'll get to that in a minute. The stack is especially quite rough to deal with at first. And truth be told, as taught most of the time, it is not aptly named. So computer memory. When we talk about computer memory, what are we actually talking about? You might think it has to do with RAM on your computer. It doesn't. No. Realistically speaking, we're talking about something called virtual memory. And the way that programs work is when you load a binary, that entire program, from the first bit to the last, is loaded into memory. But how does that work? If you have a 100 gigabyte program, say Final Fantasy or something, and you load that into memory, how can all 100 gigabytes fit into RAM? I don't know about y'all, but I have like 8 gigs on my home computer. That does not line up. Virtual memory is something that lets us have a lot more memory available to us, if you think of it that way. So instead of having just 8 gigabytes, we have, I think, 256 terabytes worth. And the most important thing to mention is that every memory address, because memory is address, can contain a single byte. Each memory address has a single byte. If you understand this, a lot of what you do in C, a lot of what you do in assembly just lines up perfectly. All those hacks that you see revolve around that concept. This is called blazingly fast for a good reason. We have a lot to get through. Now the stack. So the stack, as you know it in computer architecture, is that thing all the way down at the, I'll get to in a second why I call it down, at the, all the way up at the highest addresses of memory. So from 0 to FFFFFF, all the way down until it reaches the heap, a bit lower down. And we'll get more into where those are a bit later. So why do we call it the stack? Good question. If you take a look at what we normally do with the stack in any listing of assembly code, we tend to not actually respect it being a stack. We tend to randomly take addresses from almost anywhere inside of it and just work with them. We don't have to work at a top-down level. We don't have to say, okay, only work with the top-down stack. Why is that? Why do we still call it a stack if we don't actually treat it like a stack? We certainly push new values on the top, but if we can address anything in between, what is the point of calling it a stack? Well, here's the thing. If you take a look at individual bytes of data, then it doesn't seem very stack-like. If you take a look, it's just where it gets addressed, where you access memory, where you store memory, then it's not really fair to call it a stack. However, if you take a look and understand what a stack frame is, and how stack frames work, and how they get managed, then, well, stack is quite an appropriate name for it. So what is the stack frame? The stack frame is pretty much all of the data you keep in a function, all the local data, right? Anything that you keep in terms of local variables, arguments, and anything you need to store locally gets put into something called a stack frame. So any function call has a stack frame. And so if you think about what a program looks like, it's pretty much a sequence of function calls. You have function A, that calls function B, that calls function C. Function C will never touch anything inside B or A. It can only work with the variables it has. And so a stack frame, you can say, is completely isolated from every other stack frame. You can definitely access memory in different stack frames using pointers, but to do that, you still need to access your own stuff. And you can do a few hacks with it to access arbitrary memory, but we'll ignore that for now. That's not too important for this. So you can think of a stack as a stack of stack frames. You have the first function stack frame, and on top of that second function stack frame, on top of that third function stack frame. And you'll only ever be working with that top stack frame most of the time. If you create it like that, then assembly will begin to make a lot more sense. And reversing, actually. We'll get to that after. So how do you actually read an instruction? So assembly has a bunch of things called mnemonics. For example, a lot of you probably know add, the instruction. Add one register with the other. Or add one register with a constant. What's the register? Well, you can think of a register as a kind of hard set variable with a certain size. You have a variable, a list of variables that you can work with, and we call them each registers. You can't work with all of them. Some of them are CPU controlled, like for example, the instruction pointer. We'll get to that later. So each mnemonic corresponds to a bunch of opcodes. And if you remember, an opcode is a function. So the mnemonic is a function, and each operand are the arguments that go to the function. Now then, mnemonics are really hard to remember. It's good to have a reference handy. Operands, yeah. So what can you actually use as an argument to one of the assembly functions? Well, one, you have registers, so variables. You have the store data, load data, and you can work with them. They are very often used and confuse a lot of people because when you take a look at an assembly listing, you'll see registered used everywhere without knowing what stores what. And it can get a bit overwhelming, and you'll be able to deal with that soon enough. And so a second thing that you can have is immediates, or constants, if you want to call them. Example is the number 4. You're not going to be storing 4 on the stack if you just want to add it to a variable, right? You have int x equals 5. Where's 5 come from? That's constant. Labels. Some places in memory are used fairly often. Like, for example, if you have a string defined in memory in application, like say a hard-coded password or something, then that shows up labeled usually. And finally, you have just arbitrary locations in memory. Realistically speaking, all of these bounds of memory that we call stack frames aren't hard set by anything. If you really wanted to, you can access, well, any location memory that you want to, even the instructions, and just modify them at will. Some of them are protected, but we're not going to get into protections here. This is more of how to read assembly. So, registers. All right. So registers can get a bit confusing, but they're not too bad, honestly. When you have a register, you have your general use registers, which are the ones that you see being used pretty often, like RAX, RBX, etc. Those you usually use in the application to store data, low data. That is your variable in assembly. And you also have computer control registers. For example, the instruction pointer. When you do a Stack Overflow, you're often told that you want to overwrite the instruction pointer in order to jump to shellcode. Back in the day. Not so simple anymore, unless you work on a router. So the instruction pointer is a bit special. The instruction pointer is what we use to say CPU, what line of assembly we want to execute next. If that instruction pointer can arbitrarily be adjusted, that would be quite horrendous. Well, it can't be arbitrarily accessed, but it is possible to use things like jumps and such to go to different locations of code at will. So although assembly lets to look pretty structured, realistically speaking, you can do almost anything you want in it, which makes it slightly terrifying. But when you read it, it's pretty straightforward. So here, you have a ton of different registers that you can use. So these are some of the general use ones that we have, and it's important to note that on a 64-bit system, you have 64-bit registers, which makes sense. But sometimes you'll also see 32-bit registers, and they're called something like EAX or EBX. E at the front usually stands for extended, and it means that it'll be a 32-bit register. The way that works is, instead of having a bunch of different separate registers, all of different sizes, we tend to just stuff 32-bit registers inside of 64-bit registers to save space. There you go. Now, two important registers to keep note of are RBP and RSP. So RBP is what we call the base pointer. It points to the bottom of a stack frame. Well, yeah, so the current RBP register holds the address of the bottom of the current stack frame. And if you ever work with exploits targeting binaries, usually you know that you have to overwrite the RBP to get to the return pointer, right? Well, what's that RBP in memory? How is that different from the RBP register? Pretty much, we want to work stack frame by stack frame. So what we tend to do is each stack frame holds the address of the bottom of the stack frame underneath. So if we take that address and load it back into the RBP register, it's likely shifted to a different stack frame. And that's how it keeps up the model that works with, in terms of stack frames being functions. You can think of the moment you move the RBP down to the stack frame below, or up to the stack frame above, you essentially move to a different function. Oh, and the RSP. So the RSP points to the lowest address used by the stack. Here's a weird thing. I caught myself saying top of the stack many times when I really meant the lowest address. What you'll find pretty often is that when we say top, we really mean the place on the stack which will be added to next. Because when you think of a stack, the top is the place you add to, you push to, and you pop from. So when you say top, it's good to mean, or good to remember that it means the lower address, or the higher addresses, which is really weird naming and can throw you off quite a bit, but you eventually get used to it. Now, I already talked about the instruction pointer. Yeah, one thing to note. So the way that a lot of jump to shellcode exploits work is you want to overwrite the instruction pointer. If you take a look at a stack frame, one of the things stored on a stack frame of a function is, well, the saved instruction pointer of the last function. Say you have a function A, and halfway through A, it calls B. You want to return after B is done to where A left off. And so what you'll do in assembly is you will push the address of the instruction after the call to B to the stack frame of B. And when B finishes, it'll put that back into the instruction pointer and go to the next address of A. This is the basis of how function calls work. And the reason that we have shellcode exploits 10, 15 years ago, we still have them now, but they're a lot more complicated. The reason they worked 10, 15 years ago without things like non-executable stack and a whole other bunch of mitigations on the stack is because if you overwrote that saved instruction pointer through something like a buffer overflow, it would try to pop that value back into the instruction pointer and treat whatever it saw as code. So if you made the instruction pointer point to the stack, that code, well, that information on the stack will now be treated as code. And so you now have shellcode. And eventually they added something called a non-executable stack, which means that if you try to jump to code on the stack, it will not run. And if you've heard the way to get around it, you use something called ROP, return-oriented programming. Now, how does ROP actually work? The way that you do ROP first is instead of overwriting the return pointer to somewhere in the stack, you instead point to somewhere at near the bottom of the function, somewhere else. Call it a gadget. And so you point to a gadget, and that will return back to where the gadget was called, and it'll run the instruction after. And what if that instruction was a, apologies. So let me clarify, or let me correct that. When you have a ROP chain, you store the address of a gadget at the bottom. Underneath that is the address of another gadget. Underneath that, address of another gadget. And your stack is just gadget after gadget. And the way that you actually make this work is when you go to the first gadget, jump to that, it'll run the code, and at the bottom of the gadget is always a return. What does return do? It takes the next address on the stack, puts it into the instruction pointer, and then goes there. And so now the next address on the stack will be a ROP gadget. So you run the first gadget, and the second gadget, and the third, and the fourth, all the way until you have your fully written exploit. That's the simple overview, but it is pretty cool to know. All right, flags. So we don't want to store everything on the stack. That's not too useful. Say that you have a comparison that you make. You want to see if variable 1 is bigger than variable 2. To store the result of that on the stack when it just needs to make the comparison without the user asking to store it would be kind of wasteful. So we have a register for that, called the R flags. Now, what the R flags is pretty much a bunch of flags representing the status of the previous instruction's execution. Not all of them are updated all the time, and not all of them perfectly represent something before, but depending on what instruction you use, it will properly address and update flags as needed. One really useful instruction to know about is compare. Compare will take a look at the flags it needs to see if one of them is bigger, smaller, or whatever. If you compare variable 1 and variable 2, or register 1 and register 2, depending on which is bigger, it will update certain flags. Depending if they're equal, it will update certain flags. And then after that, you usually have a jump instruction, a conditional jump. Say you want to do jump is not equal. How does it know that two variables aren't equal? In assembly, it just has a compare and Jenny. How does that actually work? So Jenny will take a look at the flags that compare set. Depending on what jump you're doing and what condition you're jumping on, it will look at different flags. For example, if you want to jump on when two variables are equal, then you look at the flag that represents if there has been a zero set from the last operation. Why a zero? Because the way compare works is it actually subtracts one operand from the other. Right? It's a very, very clever way of doing it. And all you can do is basic arithmetic operations. Alright, now little endian. Little endian tends to mess people up really badly when they try to work with shellcode or when they try to work with checksums and that kind of thing. Because for some strange reason, every time you try to do a hex sum of the stack, or of any memory really, if you have a multi-byte value, like say an integer, it shows up backwards for some reason. Why does it do that? Well, here's the way that it works. Say you store a dead beef onto the stack. It doesn't have to be the stack, but let's say the stack for now. The way that little endian works is it says the biggest value should be closest to the highest end of the stack. The way that we usually talk about memory is from lowest address, highest address. And so first it'll show the lowest thing, lowest 2 bytes, lowest byte. First, the hex sum will show the lowest byte of the value, then second lowest byte, third lowest, all the way until it hits the highest byte, which is why it shows up backwards. So really, if you tilt your head to one side, everything looks perfectly fine. But if you don't, then it's kind of messy. And now this only works with contagious bytes. Like if you have a 4-byte value, then that's the way it stores it. But if you have a bunch of 1-byte values, then it doesn't quite work that way. So that should be good for now. We'll be taking a look at examples later on to see how we can actually use this, which is why I'm going so quickly through it. So if everything doesn't stick, that's perfectly fine, because it will make a lot more sense later. Now, data sizes. You have your byte, which is 8 bits. You got your word, which is 2 bytes. Why is it called a word? History reasons. You got a D word, which is 2 words, hence double word. And you have a keyword, which is, you guessed it, 4 words. And so those are the sizes you need to know, because when you take a look in assembly listing, if you've ever looked at one before, I imagine that you probably saw something like keyword pointer register. Something like that. And the reason that we have that is, say you want to store a 1-byte value into a 4-byte register. Or say you want to store a 1-byte value into a register, period, right? How do we tell the computer to store that 1 byte using all 8 bytes of the register? How does it know to use 8 bytes? How does it know to use 4 bytes? How does it know to use 2 or even 1? The way that it knows is because we tell it using these sizes when we make our instruction or when we read an instruction. So when you see something like keyword pointer, it means that we want to take all 8 bytes of the register up using the value that we give it. Labels already mentioned. All right. This is what a program looks like in memory, roughly. if I can go up to here. That should be good. So when you have a program in memory, it usually has a bunch of different sections. The high-level overview of it, this is for Linux binary, by the way, not exactly Windows. And this is still a very high-level view of it with a lot of detail missing, but it's the important parts. So you have your stack, which starts at 0xFFFF. That grows towards 0. You have your heap, which starts somewhere later. I say later, but really I mean at a higher address. That grows towards FFFF. At the very top of your program, bottom of the diagram, you have text, which is all of your instructions. The instruction pointer should usually point here. If it doesn't, there's probably something wrong, but not always. You have your data, which pretty much contains all of your set global variables. Say you have a global called name, right? If you set name as a global variable in your program, then it'll show up in this section over here. If you have a hard-coded password that you use everywhere for a database, it'll probably show up over here. So this is a pretty good section to know about. And if it isn't initialized, like you have string password set to nothing, it'll come up in the BSS. Calling conventions. Calling conventions will make things make a lot more sense when you actually look into them. When you're reversing using assembly, calling conventions are probably one of the most useful parts to know about. What is a calling convention? So I missed it before, but first let's talk about ISAs, or instruction set architectures, also called computer architectures. You probably know about ARM, you probably know about System V, maybe you know about 86, 64, definitely. But what are the actual differences between them? When it comes to assembly, one of the main things to know about in terms of differences between architectures is that your outputs will be different, number one. So for example, if the opcode of ret was, I don't know, say C3, that C3 would mean ret to 86, but it would mean, I have no idea what to ARM. Probably not ret. So even though a binary is made up of the same bytes for every computer that you go in, depending on the architecture, it'll interpret it in a completely different way, which is why a binary from one computer often can't trivially work on a different computer if there are different architectures. Now, calling conventions. Depending on the architecture, you probably have different calling conventions. The one that we're going to talk about today is the Microsoft calling convention, which is used in x64. So, what is it? How does it work? Say you have a function like this. It has a ton of arguments and a ton of local variables. A calling convention pretty much tells us how this function gets called, where the parameters go in the stack, where they get stored in registers, and what the stack frame will look like. So if I can show both of them, that'd be useful. Let me try zooming out a bit. Alright, that should be good. So if you take a look at the diagram, first thing to note is all of these registers that seem really arbitrary are filled up first. You have our parameters, and first, whatever fits into registers is fit here, and then the leftovers are put below the return address. Below the return address. When I say below, once again, it means towards the higher addresses. I'll say that that's how it works now. So next up, you have your return address. That's the thing that gets stored after. When you store your return address, it's pretty much what you use to return back to the old function. And return where this function is called, pretty much. Saved RBP is the save base pointer. This is where the previous stack frame begins, and where the current RBP points towards. So pretty much, you can think of the RBP as the heart and soul of the stack frame. When you have an RBP, you have a function. Or when you have a saved RBP, you have a function. Now, After that, you have a bunch of local variables. So xx, yy, zz are all stored over here. It's important to note that every variable that we can use will be stored in the stack when it's created. So the function that calls this function, myfunc, created the stack frame for us. And after that, as you'll see, when you actually get to listings, who sets up a function, who tears down a function is all dependent on the calling convention you use. And so when you take a look at the stack, it's literally just one stack frame, then the next stack frame, then the next stack frame, over and over and over again. And you'll only ever be working with the top stack frame, and at the same time, you'll only ever be working in the data of the top stack frame. So you might be thinking, well, what if you have global data? Or if you have, say, I don't know, something on the heap that you want to work with? Well, here's the thing. The way to get to the heap is through a save pointer that you have access to on the stack. So even if you're working with data somewhere else, you can only ever access it through what you have available to you on the stack. God belt. All right. So that was pretty much the introduction to assembly that I want to give. Now comes the more, well, practical part. The reason I gave that entire intro to it is because we're actually going to be looking at what assembly looks like once it's assembled line by line. Compilation failure. I can't read that there. It to the appropriate line of assembly, and I'll tell you what line means what. And it's incredibly useful for actually seeing how a C program looks like at a very low level. And it's really good for learning. So let's start off at main. First thing to note is when you take a look at this line over here, which is just the function declaration, int main open bracket, well, why does that have a ton of assembly code assigned to it? This highlighted part over here is what we call the function prologue. This is what saves the base pointer onto the stack, what puts the stack pointer into the base pointer, and then subtracts 16 from RSP. Now you might notice I didn't actually talk about what any of these instructions actually mean, which is because if we hover over it, just like that, it will give you a description, which is very useful. So push is what you think it does. It pretty much takes the register that's given and pushes its contents to the top of the stack. Move will take the value of RSP, or take the value in the second argument, which is RSP, and puts it into RBP. So remember, RSP contains an address, right? It contains the address to the top of the stack frame. What RSP used to contain was, one sec. All right, it wasn't subtracted yet. So RSP used to contain the top of the previous stack. And the top of the previous stack, in this case, is now the bottom of the new stack. And so we put RSP into the base pointer. And then we want to make space for the current stack frame, so we subtract from the stack pointer. Here's the thing. The stack grows upwards towards lower addresses. Grows up towards lower addresses. That sounds really weird. But yeah, the stack grows up towards lower addresses. Or if you want to say, that's fine. So we actually need to subtract when we want to grow it, which sounds really weird. But it makes sense. Because if you start at the highest possible address, there's no way to go but down. And so to do that, you gotta subtract. So we currently have a stack frame that is 16 bytes large. And that's what the function prologue tells us. You can think of all three of these, which you'll see at every function, in some way, shape, or form, as a prologue. I'll get to why this one doesn't have the subtract in a minute. So next up, we want to call this function add, and we want to store the result into an int. and we want to call add with the parameter of 2. All of this is done in roughly 3 instructions. So if you remember, I'm going to jump back to the previous slide for a bit because the stack train demo is really good, or diagram is really good. The first 6 parameters get stored into registers. The first one being RDI. And guess what? The first parameter is stored into EDI. The reason we store into EDI and not RDI is because RDI is 8 bytes large, while int is only 4 bytes. We don't need to use all 8 bytes of a register to store a 4-byte value, so we just store an EDI instead. And we call. So what does call do? Pretty much what it does is you save the current instruction pointer onto the top of the stack, and then you jump to the location of this label over here. So you're now in add. Then once again, you have the function prologue. Right? So this push and move you'll see over and over and over again, because setting the base pointer for the function and for the stack pointer, well, it's saving the old base pointer and it's setting the new base pointer. So it's moving to a new function. Now, after that, we just want to add 2 numbers together. Oh, sorry, I forgot to mention this thing over here. Notice that this is dword pointer, and it's quite different from most other instructions. While most of them just have instruction followed by argument, or instruction 2 arguments, this one has a dword pointer over here. Reason for that: if you remember, a dword is pretty much 2 words, which is a total of 4 bytes. And EDI is 4 bytes. RBP is 8 bytes. So we want to store a 4-byte value into an 8-byte register. Do you want to use all 8 bytes of the register? Do you want to use 4 bytes of the register? A dword pointer tells us that we want to use 4. Right? And so any time that we have the interaction between a 4-byte register and an 8-byte, we end up having this dword pointer over here. Now, when you call a function or an instruction, like add, for example, you have 2 arguments over here, AX and AX, because they're adding num to itself. Now, where is num actually? If you take a look at this line over here, EDI contains the first argument. And we want to put it into this location over here. The square brackets pretty much mean that we don't want to store it into the register. We want to store it at the location pointed to by the register. RBP contains an address, and we don't want to replace that address. Instead, we want to access it, so we can put the square brackets around it. So we're putting EDI into RBP minus 4, whatever location that is. And after that, what we're doing is we're going to take it and put it into a register. And we're going to add those 2 registers together. And that is just what we return. So what add does is it takes the first thing, EAX, and the second thing, also EAX, adds them together, and puts them into the first argument over here. So EAX now has the result of the addition. And that's all the function really has to do. So then after that, we pop the top value of the stack back into RBP. What's the top value of the stack? The old RBP. You push it, you pop it, and then you return. What return does is it pretty much puts the value at the top of the stack, which at the moment is the instruction pointer, into the instruction pointer, or the instruction pointer register. Right, so that was a function. Not too complicated. Everything actually makes a lot of sense. If you read it line by line and kind of go through it, it really isn't too bad. Everything lines up and is laid out for you. Now, you might be wondering at this point, this is all very dry. It's all very, well, low level. Why not just pop open Ghidra, open up the binary, and then look at the decompilation and have friendly C code to work with, even if it's a bit messy? Well, here's the thing. No matter what decompiler you use, you're not going to have an accurate representation of that program. You're going to have errors pop up. You're going to have times where you just can't figure anything out. And you'll just have a bunch of random decompiled lines of C that make no sense whatsoever. Sometimes it'll outright lie to you, saying that some function does something. In reality, it does something completely different. And the only way to tell reliably for us is to look at the very friendly assembly listing that it puts on the left, or somewhere else if you move the alignment of it. So assembly will tell you the truth of any program, no matter what it is. It looks really unfriendly, but really it's their best friend when it comes to figuring out what a program's actually doing, which is why it's so fundamental that you actually take the time to understand it. Now, this is over here. So here we have printf. This .lc over here is called a label. It's pretty much pointing to a string that we use very often. %b/n. Doesn't start on the stack, but it's not a label. Probably in the, not the VSS, the .data section. And here it shows up over here because we're using Godbolt. For an actual program, it probably shows up somewhere else. But once again, it depends on the AVI. Right. So how does printf work? Printf, as you can see, is actually roughly the same thing. You have, well, first let me get to finishing add. Finally, at add, after you call it, you move EAX into this address over here, RB3-4. And if you take a look at a stack frame one more time, local variables are stored over here. RB3-4 stores, in this example, a long, but for us it would be an int. And we now have x. Next up, we got printf. So printf looks a bit more complicated. It's kind of messy. But realistically speaking, it's almost the exact same thing, except now you have two arguments instead of one, and one of them's a label. So I'll use the mouse so the people on screen can see. If you have first argument, one more time, starting over here. So you want to print x, right? So x is in memory. You don't want it to be in memory. You want to work faster. So you put that into a register. And then from that register, you move it to a different register, ESI, which is the second parameter of a function. If you remember what a sec or what a calling convention looks like for x86, 64-bit. After that, we want to move the address of the string into the first argument. We don't actually need this offset flat. It's purely for us to have visual information on what it's doing. Realistically speaking, it's just moving the address of that label into EDI. Truth be told, I don't actually know what the EAX here is for both times. So we can safely ignore that for now. And then you call printf. And then you leave. And you're done. That is a very basic program in assembly. And it wasn't too bad, I don't think. Next up, if statements and loops. Actually, before I continue, does anyone have any questions? Nope, perfect. So, all right. This one looks a lot more complicated, a lot more labels everywhere. But they're used quite differently. Because before we had a label that was used to show where an important location in memory was, a string. So here we have labels above instructions, which is quite different. Here's the thing. when we call a function main, when we call a segment of code L3, or whether we call a string a certain thing, they're all labels in a way. They're for us to use to say, yes, I want to address this location of memory in a user-friendly manner. So here we have the label of main to show where main starts. And then we have all these other labels. So here, first we have the function prologue, which we can safely skip. This time we have an array of 4 bytes. Now what we do is we have a for loop. And you might notice that in the for loop, a bunch of different lines under different labels get highlighted, and they're not actually adjacent to each other. Now the reason for this is because in assembly, for loops don't make a lot of sense to put all into one block. In fact, it would be quite messy if we did that for everything. So instead, it puts instructions into a logical order of where it's best to put them. So here's what I mean. Here, first we set up the initial loop. We move forward into memory, or first we zeroed a local variable, x. Then we jump to L2. L2 compares 3 to whatever is stored in RB3 minus 4, which is currently equal to 0. And if it's less than or equal to, it jumps to L3. Hey, that looks a lot like the loop, because it is. So next up, what we do is we store whatever value as an I into xi. That's what we're doing in C at least. So anytime you see d word pointer RB3 minus 4, in your head, replace that with I. That will make things look a lot better. And on top of that, if you ever see an instruction you don't really get, and you don't really know, sometimes it's safe to ignore it and move on and see the general flow of the program, and from there see if you can actually make an understanding of what the program's trying to do. It's the same for reversing. You're not going to understand every line that you see immediately, right? You're going to start with a giant mess, and you're going to slowly, incrementally make that mess look a bit more decent, look a bit presentable. And eventually, it'll have a few clicks here and there. You're going to go, oh, this looks a lot like this functionality. And then suddenly, all those messy names that you made can line up. And instead of looking at code line by line, you can start looking at it as a group or as a block. And the same thing happens over here. Instead of looking at it line by line, you can eventually learn to skim it and go, yes, that looks like a loop. That happens when you've been reversing for a while. So here, think about arrays. Arrays are pretty much continuous blocks of memory, right? So here you have an array of ints of size 4, which means that you have 4 ints side by side. And they're all referenced by this thing called x. The first int is stored at x. The next int is stored at x plus 4 bytes. The thing after that is stored at x plus 8 bytes. And x plus 12 bytes. So you can see over here that when you have the loop, first you store I into EAX. So in your head, you can call EAX I. And realistically speaking, I don't think it's actually assigned anywhere else. So we can actually call EAX and this over here I. So this statement is actually move I into I, or call EAX I now. After that, you also put I into EDX. So EDX and EAX are both equal to I. Then you move I into this location over here. What that location is looks kind of weird because you have this weird looking equation, but it actually makes a lot of sense. You wanted to move it, or you want to move I somewhere in memory, specified by this address. What is this address? Well, you know that x is an array of 4 integers. Each integer is 4 bytes, so it is a 16-byte array. Did I do my math right there? Yeah, 16-byte array. So if I is equal to 0, yeah, is less than 3? No. All right, then. In that case, actually, it still is less than 3. One more loop. Now I is equal to 4, bigger than 3, so we don't jump. This means jump if less than or equal to. And it depends on the comparison up over here. So this is saying compare I and 3. If I is less than or equal to 3, then jump up over here. Else continue on. Now we finish the loop, so we move on to the next line. We set I to 0. A different variable I. So this is at RBP minus 8. So in your head, every time you see a D-array pointer, RBP minus 8, you can just say this is I. Now we have another loop, so we jump into L4. Right. So this loop is a bit different because it's the while loop. But realistically speaking, it's the same as a for loop. The only difference is in terms of the syntax that we use. So once again, you have your array called x at the same location. So d-word pointer RBP minus 32 is x. Once again, you compare the first element of x to 3. While the first element, because this thing over here points to the first element of x. An array is really just a fancy pointer. You're saying, all right, I have 4 elements over here. I want x to point to those 4 elements. And I'll show you how that works in more detail in a bit. And so you go through your loop, and that's the while loop. Roughly the same, except now you jump if ex and 4 aren't equal. Actually slightly different from being less than or equal to 3, but it works pretty well. Now we have if statements. Now, if statements are usually, well, they look a lot like loops, except without the looping part. So you don't have any counter anywhere, you don't have any condition to leave. It's more of a, we're not going to go up, we're going to go down. A loop in assembly will go up and down and up and down. An if statement will just go pure down most of the time. So here, once again, this is the first element of x. We move that into EAX. So now we can say EAX is x0. Compare that to 4. If it's not equal, then you go to L6. So if it's not equal, then you go down to this line over here. Else, you return 0. L9 is just returned. When you go to L6, once again, x0 into EAX. You compare that to 5, it's less than 5. Then you go to L8, which is the true condition. Else, you go to L9. And that's what loops and ifs look like in assembly. All right, last one. Pointers. This one you can probably find on an exam somewhere. It is complicated as heck, but it's also quite beautiful. Wait, no, this is not the one I was looking for. Arrays was the one I was looking for. Actually, let's do this one too. So let me look at the time really quickly. We have about half an hour left. All right. I should wrap this up quickly because I want to get the geeter after. So here, pointers. when you're dealing with pointers, one thing that you're going to encounter often is called LEA, and this tends to confuse the heck out of people. Because what's the difference between move this and LEA this? Well, here's the thing. When you move, you're saying, okay, I want to move the value found in the location RBP minus 8 into here. When you have LEA, you're saying, all right, RBP has an address. I want to subtract 8 from it, and I want to store that address into RDX, the thing that we calculated. So when you calculate something and want a pointer, then use LEA. But if you want to move the thing that it points to into register, then use move. So LEA is like an actual ampersand, and move is like a dereference, if you want to think of it that way. All right, and then let's go to bad swap. So once again, this looks really complicated, but it really isn't too bad. So the way that we pass pointer arguments to a function is literally the exact same as how we pass any other argument. And you'll find that there really isn't any magic in assembly, or most of the time, until you get into the hacky stuff. Well, in normal domain, whenever you want to pass an argument to a function, you pass that argument into RSI, RDI, all different normal parameters, normal calling convention. Whenever in doubt, look at the calling convention and you'll understand what is inside of a function. All right, and then we call bad swap using the 2 pointers. So let's see. Remember, RDI and RSI contain pointers. They don't contain actual direct values. And so we want to store them into the status over here on the stack variables, or their parameters. And we want to store them into a keyword pointer because pointers are 8 bytes, so we need a keyword. Now that we store them, all right. First, it looks like we're moving one of them into RAX, and then we're moving what's happening over here. So we stored the pointer into RAX, and then it looks like we're putting RAX into EAX. But at the same time, we're using this over here. Because if you look at the line of code, we're dereferencing X. And if you remember what this over here does, it pretty much means instead of taking a look at the value inside the register, I want to look at the value of where it points to. So this is the dereference. RAX has the pointer, you dereference it to find the value, and you store that into EAX, which is an integer. And that's the main thing I want to show over there, how to deallocate a pointer. And when you assign the value of a pointer, it's roughly the same thing. You want to deallocate it, and then you want to assign the value. It's pointing to somewhere on the stack or on the heap. So when you deallocate the pointer, it'll give the address of that location in the heap or on the stack. Right. Now for the fun one. And this is the last one I'm going to show. If you want to do structs, it's possible to do them on your own time. It's also not too bad. Now, this looks really complicated. In fact, I'd like to bet that if you took a look at it, just at the normal C code, it's very hard to understand what's going on. Right? Because over here, you have an array of 4 values, 2, 2, 3, 4. Or 1, 2, 3, 4. What you do first is you set the first value equal to the second value. So now you have 2, 2, 3, 4. Then you set the first value to the dereference of X. Oops. What does that actually do? If you remember, X is just a fancy pointer. It points to the first element of the array. So if you dereference X, it's going to give you the first element of the array. So you set x1 to itself. Next up, you have a pointer to an int y that points to the third element of the array, 3. And then you're setting the third element of the array to y minus x, a pointer subtracted by a pointer. Now, what do you think this actually calculates into? Or what does this actually resolve into? Well, if you take a look at how memory addresses work, you can say that x points to something, and then we want to go 3 increments over. So this would be about 12 bytes after. Now you might think, okay, that means that x2 is equal to y minus x. The difference is 12 bytes, therefore it's equal to 12. But that's not the case. Here's the tricky part about C. When you define a type, it'll cast it to that type. And so when you subtract 2 pointers, it'll cast that value into the actual physical distance, which is 3. It's not intuitive at all, but when you understand casting a bit more, it once again makes a lot more sense. And finally, to show that x actually is a lot like a pointer, you go to x plus 2, and because x is an int, this actually moves 2 int values over, so 8 bytes. So x3 is equal to x2. So your final value is 2233. And when you call a function, you get x assigned to 0, once again, 0233. All right. Now, at the bottom, we also have structs, but this example will take a lot longer to do, and we don't have a lot of time. So instead, we're just going to jump to Ghidra, which I find to be of a lot more value. And at the bottom, if you want to know more about assembly, and if anything, go to this website over here. This place is amazing. Not just for assembly, but if you even want to learn about, for example, like, let's say, heaps and such, return-oriented programming, and then some. It is a fantastic resource for anything you want to do, especially if you want to get into ARM. Now, Ghidra. I never actually took a look at this binary. I found a random trackme and said, all right, I'm going to show how you start a Ghidra project from 0 to getting whatever you need. And I'm not going to look at anything ahead of time because I want to do it the way that I do it and show the process of fumbling around until you finally understand. First and foremost, you want a project. And what a project is what you think of as a project in normal software engineering. A bunch of files all together made to do something. Say you want to look at, let's say, a small program that you made that just has a hello world.c file and a run shellcode file for whatever reason. Then you'd make a project for both of them and import both of them, and you are able to work with both of them in a really nice way. So first you create a project. If you want to work with someone, you can make it shared, but we're not, so we're going to do non-shared. And we're just going to keep the defaults of, let's call it, we're going to call the project TrackMe. So now you have the folder over here, but no files inside of it. To import a file, you literally just press I, and it opens up a window. So I have it downloaded to my USB. All right, let's hope I remember where it is. Probably on Mount. If not Mount, then Media. Not Media either, not that I can see at least. All right, I'm going to move it onto the desktop really quickly. Right. So desktop license checker. So it's going to ask you about the format of the file. If you're working on Linux, they're going to do ELF, and if you're working on Windows, it'll probably be PE, and it should fill out by itself for you. Language, as you know, x86 is the architecture, little endian, 64-bit, default stuff, and GCC. So all those values actually make sense when you look at them. Destination folder is the project folder. You're going to make a track me, and here's the program name. And you're good to go. And this is just a summary of everything. You don't have to look at that. Now you have it here. Double click it. Or if that doesn't work, click the dragon. You have to analyze it again. So I don't have access to the entire screen, which is a bit of a problem. So I'm going to make it smaller, actually. There we are. So we don't actually have a listing over here, which means it didn't analyze properly. So I'm just going to close the tool. And I am going to actually delete this one time. I really hope this doesn't delete the binary, but it should be fine. All right, let's import it one more time. Okay, we're good. Ah, that's why. Okay. Open the dragon. And I remember why. We didn't actually analyze the binary. And from what I can see, it didn't actually load the binary. Which is a problem. We don't want to do that. That's not quite good. But it already exists, which is weird. So let me see if I can find it somehow. There we are. So it says it hasn't been analyzed. You're going to want to analyze it. You're definitely going to want to analyze it. This is how you get your disassembly stuff, and this is how you get it to make a smidgen of sense at the beginning. So the defaults are usually pretty good, and as you work with more strange binaries, you're going to figure out what these flags do. But for now, you can just hit analyze. And we're good to go. So this, if you want to jump to a function, double click. Here's what you're presented with. Really funny looking window. You have param1, which is an int, and param2, which is an undefined date. Here's the thing. When you take a look at a type in Ghidra, and it says something like undefined 8, this means that it doesn't know what the type is, but it's 8 bytes. And we can probably infer that it's 8 bytes because it's a pointer, but we don't know what pointer or what it's pointing to. We do know, though, that when you have main, you usually have 2 arguments to it. You have your argc and argv. And over here, we can see you have an int, so it's probably argc, and we have a pointer, so it's probably argv. And we know that's a char pointer, so we can actually retype it. And even if you're not sure, even if it's just a guess, it's always better to guess and rename things as you go on than it is to have nothing named and nothing marked down and continue going in reverse. Because they're going to get lost very, very quickly, and your guesses will eventually converge to an actual program. So let's retype it, and let's rename it, actually. So to rename something, you press L, and you can give it a name. Let's call it argc. And updates, and let's call this argv. And if you want to retype it, right-click and retype variable, which is also Control L. We are going to make it I want to guess that it's the car pointer. I'm not completely sure though. Let's see what happens. It's retyping it. If you take a look over here, when we added a type, it recast it to something else, a car double pointer, and then dereferenced that once. So it might be likely that argv is a double pointer, which if I remember correctly, it actually is. So it's not too bad if you accidentally make a mistake, because you can fix it really easily. And when you look at that, this looks really nice. So we're trying to find the string length of argv1, and that would be the first argument. Now, we're going to actually run the program and see what it does, because I am not too sure. Apparently, it's trying to look at the length of the first argument for something. And it takes two arguments, and the first argument is always the binary name. And so I'm guessing, if the usage is correct, that the second argument is the license code. So to make an educated guess, we can say this is license length. That looks reasonable enough. And it looks like it's a size t, but it's an int. Let's be real. It even gets cast int over here. So we can just retype that as an int. And it looks a lot cleaner. svar2. Did I accidentally rename the wrong thing? Or retype the wrong thing? If you ever make a mistake, you can press Ctrl Z, and it does undo. Oh, that's really weird. So if I retype license length, it doesn't work properly. Or it ends up creating a variable. Let's see if this will help. Int. Nope, it creates a new one. Wow, that's weird. Okay, so if it does something like that, then it's usually better not to retype it and to leave it as is, because it's much better to work with things you understand versus things you don't. Now then, so we seem to have a loop over here, and we want to see if the length is less than or equal to local 14. And local 14 seems to get incremented once at the end of the loop every time. So it looks like we have something that can be called a for loop almost. Because license length never gets updated. And local 14 goes up by 1 every time and starts at 0. So this looks like a for loop going from 0 to license length plus 1. So we can call local 14 I for now. And this makes sense, kinda. Now, what does the loop actually do? So local 19 is equal to argv1 is the license, and we want to take the ith index of it. So since we go from 0 to license length, this looks like a character. Local 19 is the character, so we can retype it. Oh, it's already a character. And on top of that, it looks like it's representing, it's going through each character of the license that you give it, character by character. So we can call this char I, or something like that. If let's be verbose, char I of license. So it looks like ivar1 turns the character into an integer. And then local 18 looks like it's the sum of all of these integer values. All right, so let's call ivar1 Hmm, sum of car codes. Oh, sorry, let's go local 18 sum of car codes. This is equal to car code. Yeah. And this will be equal to sum of car codes. Alright, that makes sense so far. And now it looks like if the car codes sum to exactly 32 in hex, and if you hover over 32, I'll give an actual decimal value, 50, then we get premium access. Otherwise, we have the wrong code. And I don't actually know what this line over here does, but it looks like local 10 isn't actually used anywhere, so we can safely ignore that. Probably. So now what we probably do is we would most likely go and make a script that would sum up a ton of car codes until we get to 50 with a license length of, actually, you know what? There's no restriction on the length of the license. So technically we can just get a even value thing. Here, let's do this. So we're going to take a look at all the car codes. Our ASCII integer values. ASCII table. All right, we want to get a license that sums up to 50. What if we just get an ASCII character with 50 as a value? That would be 2. So if this is correct, if we just enter 2, we should get premium access. Hypothetically. Let's see if that actually works. I want terminal. Oh. Two. Nope. 2 is not good enough. So let's see what we did wrong. All right. So we convert license length isn't it, so that's perfectly fine. We get the 0th element, which should be 2. And then we turn it into an integer. So what would a to I of 2 be? What does a to I actually do? It should be asking to integer. And then if the sum is equal to 32, we should have premium access. Sum of car codes is equal to, well, it's equal to 0 plus whatever value 2 has. And then it should exit. Because 1... Oh, wait a second. What is license length? If we have a license besides 1, then this loop actually runs twice, doesn't it? Yes, it does. It does run twice. And then, on top of that, what's being added onto 2 that makes it not equal to 50? What comes after a character in the string? Should be the null byte. So let's take a look at what value the null byte has, if it even has a value. I mean, it should be 0, right? So I should just technically add 0 to it. In that case, I'm not too sure. Let's double check what A2I does. Character temperature. Let's see. Value of type int. Doesn't really matter too much. Alright, not a problem. Yep, enter a number, F gets. Oh. Oh. Okay, A2I just takes the number and turns it into its integer representation, not its ASCII code. There you go. So technically, if we enter 50, nah. Alright, it's not 50. Which is weird. So A2I should return. Yeah, A2I should give us back 50 if we enter 50. Oh no, it takes each character of the license and adds them together. So we have to give digits that add up to 50. All right, there you go. So let's do 9, 18, 27, 36, 45, 50. I hope this works. Perfect. And that is how you solve a cracking using Ghidra, along with the debugging that goes with it. Oftentimes you're not going to do it perfectly, but that should give a good overview. And if you ever want to look into a function to see what it does, then you can just double click it. We don't have string length because it's a library function and it's not statically compiled. But if we have something else like main, double click, enter, reverse. And then whenever you need to, you can actually rename a function too. Inside main, we can call it, let's say, so through a combination of renaming and retyping, creating types when you need to, by creating structs, and looking around for what you want and making sense out of things. Reversing ends up becoming not trivial, but a very fun challenge. And to pass us back into assembly, here you can see it says license length int, and you bring it over here, jump to this label. Pretty much, the program's a bit too simple, so it's pretty straightforward. But if something doesn't make sense, then you can look at the assembly and kind of get a gist of what it's doing. Like over here, we can see that argc and argv are parameters. And here we can see that there's something being stored over here that we're bringing to RX for whatever reason. And we're also storing that as a local variable. But in this case, it doesn't matter too much. So we have reversed it completely. You have gone through a very, very breakneck speed mini course on assembly, learned about architectures, calling conventions, and whatever else you really need to know to truly understand what's going on when you reverse. What you can probably do next is open up Ghidra, open up a few applications, and see what you can do. Reversing's a lot of fun. Do more of it. All right, we're almost out of time, but one last call. Any questions about anything? Nah? Cool. Thank you for your time.
All right, thank you, Emil. So that's it for the workshops today. Now is sort of your free time to solve challenges and network.